Okay, so let's take a look at a problem like 9x to the fifth plus 63 x to the fourth plus 108 x to the third. So if we're asked to factor this, the first thing we always look for is a greatest common factor. Now this one, we know that there's a common factor just by looking at the variables because x is in every term. So we know that there's going to be a common factor. We just now need to figure out what it's going to be. For the numbers 9, 63, and 108, is there a common factor there? 9, very good. So 9, and then how about for the x, the variable? X to the third, good. It's always the smallest power of the variable. So to figure out what's left, we're going to divide that whole thing by 9x to the third. What's it going to give us? X squared plus 7x, good, plus 12. Are we done now? Okay, yes, we can. Second step, of course, once we've done a greatest common factor, or if we haven't been able to find a greatest common factor, depends on whether it's 4 terms or 3 terms. 4 terms, of course, as we would try the grouping. 3 terms, we try to do that reverse multiplication. Or reverse FOIL, if you will. So the x squared plus 7x plus 12 might be able to be factored more fully. Now we're going to have to remember at some point to bring down that 9x to the third, so I'm going to do that now. For factoring x squared plus 7x plus 12, what do we know it's going to be down in our factors down here? Perfect. X is going to be the first one in both so that we get the x squared. What else do we know? Perfect. We need to find 2 numbers that multiply to make 12, but then also the outside and inside products are going to give us that 7. What do you want to try?
3 and 4.
Positive 3 and positive 4. Good. Now we knew 12 is positive, so we know that either both of those are positive or both are negative. The 7 is positive, which tells us most likely both of them are positive. Let's double check it. On the outside, x times 4 is 4x, and on the inside, 3 times x is 3x, and that adds up to 7x, which is what we want. So yes, that factors to 9x to the third times x plus 3 times x plus 4. We talked about special products. One of the special products we looked at is a perfect square trinomial. So we need to be able to identify a perfect square trinomial, and then also break it down into what that binomial is that we square to get it. So I might have x squared plus 24x plus 144. Is that a perfect square trinomial? How do we know?
Well, I know 12 times 12 is 144, and 12 and 12 gives 24.
Okay. So you factored it, and you came up with the same two factors. And that is a perfectly good way of doing it. We know that this is x and x to make x squared. To make 144, we might try 12 and 12. And if we double check that, we have 12x on the outside and 12x on the inside gives us the 24x. So having x plus 12 times x plus 12, we know that that is x plus 12 squared. So that's a perfectly fine way of going about factoring that out. As we look at this, we can identify, without having to factor it, we can identify that it is a perfect square trinomial. What we do is we take the square root of this first term, the coefficient of that first term, I should say. This coefficient of that first term, since it's just x squared, is actually a 1. What is the square root of 1? 1. Perfect. The third term is 144. What's the square root of 144? 12. Good. Now, for this to be a perfect square trinomial, both of those coefficients, the first and the last, had to be perfect squares. To finish it off, that middle term has to be 2 times the square root of the first one, times the square root of the last one. So 2 times 1 times 12 is 24. So that helps us identify this as a perfect square trinomial. So can you identify, is this a perfect square trinomial? Okay, so what is the first term? What's the square root of its coefficient? Square root of 25 is 5. Last term is a 9. Square root of 9 is 3. So we've got 5 and 3. We've got 2 times 5 times 3 makes 30. That is correct. So remember, the 5 comes from the square root of the first term, 3 comes from the square root of the last term, and the 2 is just a constant that comes in there because of that FOIL process. Let's try another one. Is that a perfect square trinomial? Well, let's double check it. What's the square root of our coefficient on the first term? What's the square root of 16? 4. Last term's 49. What's the square root of 49? 7. So now we're going to do 2 times 4 times 7, which gives us 56. This is not a perfect square trinomial. Doesn't give us that middle term. Would the negative have bothered us? Let's look at one where we've got that negative. 4x squared so 4x squared plus 36x plus 81. So the square root of 4 is 2. Oops. What's the square root of 81? 9. 2 times 9 is 36. Positive. Does that mean it's not a perfect square? It is still a perfect square. It is we got 2 in the front and 9 in the back. What it means is this is 2x. Instead of plus 9, it is minus 9 squared. Whereas if we went up here, this is a perfect square trinomial. The square root of the 25x squared was 5x squared. Square root of the 9 is 3. That's positive, so it's just 5x squared plus 3 squared. Does that make sense? So I'm going to have you try one here. Factor nine x squared plus 66x plus 121. So what I typically do is I start the factoring process. And then as I'm factoring, I check to make sure that it really is a perfect square trinomial. I'm looking at this and it looks like a perfect square trinomial. Let's test it. So that first term, the 9x squared, what is the square root of 9x squared? 3x. Last term's 121. What is the square root of 121? 11. This is positive, so this would be plus. What is 2 times the 3x times 11? 66x. That is that middle term. So this is a perfect square trinomial, and that would be its factoring. How many of you had the 3x plus 11 squared? How many of you just needed a couple more minutes? Okay. I'll have you try one more here. Try that one. First thing we notice here, of course, is that we can take out a 5x, a common factor. So we divide that by 5x, what is left? 4x squared, what's next? Plus 12x plus 9, good. So if that is a perfect square trinomial, the 5x is still going to be there. Let's split it up. That first term, 4x squared, what is the square root of 4x squared? 2x, good. Last term is 9. What's the square root of 9? 3. Would this be plus or minus? Plus. Now let's double check. 2x. 2 times 2x times 3 gives us 12x. That is our middle term, so that is correct. This is a perfect square trinomial. So that gives us the 2x plus 3 squared, and then we still have the 5x with it. What do you think? Not too bad? Is this a perfect square trinomial? Well, the powers look weird, don't they? But what is the square root of x to the fourth? X squared. Good. Remember, when we square root, we divide the powers by 2. When we square, we're multiplying the powers by 2. What is the square root of 9? 3. If I do 2 times x squared times 3, what do I get? 6x squared. This is a perfect square trinomial. It's x squared plus 3 squared. It's something called an equation that is in a quadratic form. What quadratic form means is that this last term has no variable or has a variable of the appropriate power. This middle term, its variable, and the variable in that first term, the power of the first term is double that of the second term. So it could be something like x to the 8th plus 12x to the 4th plus 20. Now this is not a perfect square trinomial, but it is in quadratic form and it is factorable. Because this term has a power that is double this term, the variable in that second term. So just like I did with other trinomials, instead of being x times x, of course, this will be x to the 4th times x to the 4th. What I'm going, I put the wrong number in there, didn't I? This should be a 35 over here to make it factorable. What am I going to split 35 up into? 7 and 5. If I double check this, on the outside I have x to the 4th times 5, which is 5x to the 4th, right? On the inside I have 7 times x to the 4th, which is 7x to the 4th, and that adds up to 12x to the 4th. That's that middle term. That is a proper factoring of x to the 8th plus 12x to the 4th plus 35. We can run into things like this. X squared plus 5xy plus 6y squared. This looks different than what we've been working on, but it's still in quadratic form. The variable in the first term has double the power of the variable in the second term. X squared and x. It also gets reversed with the second and third term. There's a variable in the third term. We haven't had that before. The variable in the third term has double the power of that same variable in the second term. Y and y squared. So if we go to factor this, of course, x squared still has to be x times x. The y squared still is going to be y times y, just like x times x, but we have to put in the number, things that multiply to make 6. 1 times 6 or 2 times 3. What do you want to try? I heard both. Let's do the 1 times 6. So on the outside, we have x times 6y is 6xy. On the inside, 1y times x, which is xy or 1xy. That adds up to 7xi. Not quite what we want. Let's try the 2 times 3. On the outside, x times 3y is 3xy. On the inside, 2y times x, 2xy, which adds up to 5xy, which is what we want. So that is x plus 2y times x plus 3y. So in our perfect square trinomials, we can end up with variables in that third term as well, and it doesn't affect our process. It's still going to be the same. So the first term, 9x squared, what is the square root of 9x squared? 3x. The third term, the last term, is 25y squared. What's the square root of 25y squared? 5y. So to check the middle, 2 times 3x times 5y, what's that multiply out to be? 30xy. So this is a perfect square trinomial. I've already done all the hard work. What's my first term here have to be? 3x. My second term? 5y. And plus or minus? Plus. So we might have 36x to the 8th minus 120x to the 4th, y to the 3rd, plus 100 y to the 6th. Now, first thing I want to do is I want to verify, is this in quadratic form? Yeah, going this way, I have x to the 8th and x to the 4th. Going the other way, we have y to the 6th and y to the 3rd. 3 is half of 6, 4 is half of 8. So we're good in that direction. I'm going to give you a second. I want you to try to factor this one in your notes. The square root of our first term, the square root of 36, x to the 8th, is going to be 6x to the 4th. Good. Our last term, 100y to the 6th, the square root of 100y to the 6th is 10y to the 3rd. Good. Now to see if this is a perfect square, 2 times 6x to the 4th times 10y to the 3rd is 120x to the 4th, y to the 3rd. That's sort of what we want, but that's negative. So that being negative tells us it has to be 6x to the fourth minus 10y to the third squared. Any questions there? Okay, one of the other special products we looked at was a sum and difference product. A sum and difference product came into play when we had two terms that were the same, but one was a sum and one was a difference. So we might have 5x plus 7 and 5x minus 7. And what we found is when we multiplied this out, we got a very distinct pattern. So if we do our FOIL, 5x times 5x is 25x squared. Good. 5x times negative 7. Negative 35x. On the inside, 7 times 5x. 35x, or positive 35x. And 7 times negative 7. Negative 49. And when we go to combine stuff there, we have the 25x squared. Negative 35 and positive 35 cancel out, and we have minus 49. This result was what we referred to as the difference of perfect squares. And the shortcut that we noticed was to get that result when we have a sum and a difference product. It's just the first term squared. 5x, if we square that, is 25x squared. The second term squared. 7 squared is just 49. And of course, it's subtracted. It's a difference. So if I had 3y plus 5 times 3y minus 5, what's that going to give us? You got it. 3y squared, 3 squared is 9, y squared is y squared, minus, because the difference, 5 squared is 25. Very good. 9y squared minus 25. So we need to be able to recognize how to go the other direction. And we need to first be able to look at something like this and identify that it is the difference of perfect squares. So if I have x squared minus 225. The first term here, x squared, is that a perfect square? Yes. What is the square root of x squared? Just x. Is 225 a perfect square? Yeah, it's 15. So those are perfect squares. This is a difference of perfect squares. And it's going to factor into that first square root was x plus the second square root is 15. So x plus 15 times x minus 15. Is this the difference of perfect squares? Yeah, what is the square root of y squared? Y. What's the square root of 81? 9. So that's going to become, what are my two products going to be? Oops, I did the square root of y squared. That should be actually the square root of y to the fourth is going to be what? y squared. So my two products should be perfect. Y squared plus 9 and y squared minus 9. Now I threw this problem here a little early in the game on our difference of perfect squares. But does anybody see an issue with those two factors we just got? Actually, one of the two factors we just got. Yeah, this one, y squared minus 9, is still the difference of perfect squares. The square root of y squared is y. The square root of 9 is 3. So the y squared plus 9 cannot be factored. That's called a sum of perfect squares, and a sum of perfect squares can never be factored. But the y squared minus 9 is a difference of perfect squares. It can factor into y plus 3 and y minus 3. So there is our factoring of that. Is that the difference of perfect squares? It is. The square root of 49x squared is 7x. The square root of 1 is 1. So that factors to be what? Perfect. 7x plus 1, that's our sum. And 7x minus 1, that's our difference. It becomes that sum and difference product. Is that the difference of perfect square? Oops, first of all, it's not a difference. Is that the difference of perfect squares? No. X to the fifth is not a perfect square. To be a perfect square, the variable has to have an even power. Is that the difference of perfect squares? No, 80 is not a perfect square. 81 is, 80 is not. Is that the difference of perfect squares? 4x to the 12th is a perfect square. 9 is a perfect square. So what's wrong with this? It's not a difference. It's plus. It's a sum. So all three of those are traps that you got to avoid falling into. Be careful with them. Is this the difference of perfect squares? It doesn't look like it, does it? But what can we do to this? We can divide out a common factor of 2. Both 8 and 50 are divisible by 2. What do we get when we do that? Perfect. 8x to the 6th divided by 2 is 4x to the 6th. Negative 50 divided by 2 is negative 25. Now it's apparent that that is the difference of perfect squares. 4x to the 6th minus 25 is going to factor into what? Perfect. 4x to the 6th Square root is 2x to the third. 25, the square root is 5. So 1's plus and 1 is minus. There it is. I'm going to have you guys try one in your notes. Give that one a shot. So the first thing we notice here is what? You can get out a 28x. Good. Once we divide by 28x, what do we get? X to the fourth minus 25. And now, of course, x to the fourth minus 25 is pretty obviously a difference of perfect squares. What is the square root of x to the fourth? X squared. So x squared and x squared. What's the square root of 25? So 5 and 5. So plus 5 and minus 5. Any questions? A couple of special products that we have not looked at involve perfect cubes. We're going to multiply out this problem right here. A plus b times a squared minus ab plus b squared. So I'm going to start with the a. What is a times a squared? A to the third. Good. What is a times negative ab? Minus a squared b. Very good. What is a times b squared? ab squared. Now we go to the next one. What is b times a squared? A squared b or ba squared? What is b times negative ab? Minus ab squared. Good. And b times b squared? Plus b to the third. So when we go to combine here, we've got our a to the third. Those cancel out. Those cancel out. And we have plus b to the third. What we have here is called the sum of perfect cubes. Sum, of course, because it's plus. Perfect cube because a cubed and b cubed. So the first step is to recognize this form, a cubed plus b cubed, and work from there. That is the sum of perfect cubes. Obviously, x cubed is a perfect cube. If it's a power other than 3, to be a perfect cube, the power has to be divisible by 3. So 3, 6, 9, 12, 15, 21, and so on. 27 is a perfect cube. What number cubed gives us 27? 3. Good. So we have x and 3. Now remember up here it was a and b, right? So a is going to be x and b is going to be 3 here. And the form we had was a plus b times a squared minus ab plus b squared. So a plus b is going to be x plus 3. A squared is going to be what? X squared. Minus AB. Will be a minus. What's a times b here? 3x. So minus 3x plus b squared. 9. Perfect. So x to the third plus 27 is x plus 3 times x squared minus 3x plus 9. Let's do another example. 8y to the third plus 125. This is a sum, it's plus. Are those perfect cubes? The cubed root of 8 is 2. Cubed root of y to the third is y. What is the cubed root or third root of 125? 5. Very good. So as we factor this, a is going to be 2y, b is going to be 5. Remember, our form is a plus b, a squared minus ab plus b squared. So what's going to go in here? 2y plus 5. Very good. What's the first term going to be here? Yeah, a squared, 2y squared, 2 squared is 4, y squared is y squared. Second term. It's going to be minus, and again, 2y times 5 is going to be 10y. Our last term? Plus 25. Very good. So 8y cubed plus 125 factors into 2y plus 5 times 4y squared minus 10y plus 25. Let's have you guys try one. Y to the ninth plus 512. So what is the cubed root of y to the ninth? You divide the power by 3. Y to the third. What's the cubed root of 512? 8. So we have a equals y to the third and b equals 8. So what's our first piece here? Y to the third plus 8. Very good. What's the first term of our next piece? Y to the 6. Remember, it's a squared. Now it'll be minus a times b. What's that piece going to look like? minus 8y to the third, good. And then, of course, plus b squared, which is going to be plus 64. I wasn't very nice here. Can anybody tell me why I wasn't very nice? Cubed root of y is y. Cubed root of 8 is 2. That's also the sum of perfect cubes. That factors into y plus 2 times y squared minus 2y minus 4. Then we still have that last term, y to the 6th minus 8y to the 3rd plus 64. If you made it this far, I'm proud of you. If you made it this far, I'm impressed. Did anybody get to this second one, this last piece? Okay. Like I said, I wasn't being very nice there. But it gives you an example. You can really get down a rabbit hole if you have like x to the 81 plus 1. X to the 81, that is a perfect cube. What is the cubed root of x to the 81?
27.
X to the 27, good. What's the cubed root of 1? 1. So that's going to give us x to the 27th plus 1. What goes in here? X to the 54. Good. When we square an exponent, we multiply the power by 2. Minus 1 times x to the 27th is just x to the 27th. Plus, 1 squared is just 1. But you may have noticed that's perfect cubes. The cubed root of x to the 27th is x to the 9th. And the cubed root of 1 is still 1. So we've got x to the 9th plus 1 times x to the 18th, right? X to the 9th squared minus x to the 9th times 1 is just x to the 9th plus 1. And of course, we still have that. Oops. Mess. Now you might notice something here. X to the 9th is still a perfect cube, isn't it? Yeah, I would never quite do this to you on a test, but the cubed root of x to the 9th is x to the 3rd. So you could factor that. And to really top it off, that can still be factored. With all those terms after it yet. Like I said, I wouldn't be that mean to you, but it is possible, especially when that other term is a 1, because you can take the root of 1 as many times as you want to. Any root of 1 is just 1. So you can really get down the rabbit hole with those. It can keep repeating. The next one we want to look at is when we multiply out something like this. A minus b times a squared plus ab plus b squared. So we start out, we've got a times a squared, which is a to the third. A times AB, which gives us a squared B. A times B squared gives us AB squared. Good. Now we move to the next term. Negative B times A squared. Negative A squared B. Negative B times AB. Negative AB squared. And negative B times B squared. Negative B to the third. If we add those up, we got A to the third. A squared B and negative A squared B cancels out. AB squared and negative AB squared cancels out. We have minus B to the third. There you got it. You found the pattern. This is perfect cubes, but it's subtraction, so it's a difference of perfect cubes. I often just call it a difference of cubes, but technically you should call them perfect cubes. And it fits that pattern. A to the third minus B to the third, or A cubed minus B cubed, is going to factor into A minus B times A squared plus AB plus B squared. So we might have x to the third minus 8. What's the square root of x to the third? Just x. Good. What's the square root of 8? Or sorry, not square root, the cube root of 8. 2. So it's going to go over here. We have x minus 2. A is equal to x and B is equal to 2. Now this is going to be a squared plus AB plus B squared. So what's this first term going to be? X squared. Yeah, if A is x, then A squared is just x squared. What's our second term? 2x. Good. A times B is just x times 2, or 2x. And our final term? 4. Good. If B is 2, 2 squared is just 4. So we might have y to the third minus, let's make it more interesting than that. Let's do 125y to the third minus 64. What is the cubed root of 125 y to the third? 5y. You got her. What is the cubed root of 64? Just 4, right? So over here, what's this first factor going to look like? 5y minus 4. Good. And our second factor, what's the first term going to be? 25y squared. Good. We square this one. What's our second term going to be? Plus 20y. It's just, we multiply 5y times the 4 is 20y. And our last term? Plus 16. So we got 5y minus 4 times The 25y squared plus 20y plus 16. Now, when we get to this point, this sure looks like something that should be factorable, doesn't it? I will let you off the hook. It never is. The only time that is ever factorable is if there was a common factor that we could have taken out here first that we didn't. So you've got to be careful for that. So let's do 28 x to the 11th minus the brain's shutting down on me. 28 ain't going to work anyway. I've got to do 56x to the 11th. And 189x to the 2nd. Tell me what to do here. First, we see that there is a common factor. They both have x's in them, so I know I can factor out at least an x squared, right? Is there a common factor in the numbers? This is a tough one. Right now, neither of those numbers are perfect cubes, are they? So our hint would be that they're not perfect cubes, so we would hope that there is a common factor that'll make them perfect cubes. Well, smaller than 56, the only perfect cubes are 27, 8, and 1. Can I divide by something to turn 56 into 27? No, right? Can I divide by something to turn 56 into 8? 7. Can I divide 189 by 7? Yes. So let's divide by 7x squared as a common factor. 56x to the 11 divided by 7x squared is 8x to the 9th. Good. Negative 189x squared divided by 7x squared is negative 27. Now this, oops, did you have a question? Now this is the difference of perfect cubes. What is the cubed root of 8x to the 9th? Two x to the 3rd. Good. Cubed root of 8 is 2, and then you divide the power by 3 to get x to the 3rd. What is the cubed root of 27? 3. So in our solution, we got to remember the 7x squared. What's our first term going to look like here? It's a minus b, right? So 2x to the 3rd minus 3. Then our next term, remember, it's a squared minus or plus ab plus b squared. So what's a squared going to be? 4x to the 6th. Good. 2 squared is 4. X to the 3rd squared is x to the 6th. Plus, what's that middle term going to be? 6x to the 3rd. Good. 2x to the 3rd times 3 is 6x to the 3rd. And my last term? 9. 3 squared is 9. So that's what we get. I would recommend that somewhere in your notebook you make a formula sheet with these, the perfect cubes, the difference of perfect cubes, sum of perfect cubes, the difference of perfect squares, the perfect square trinomials, so that you have it. I usually tell people pick the last page of your notebook or the inside of the back cover of your notebook so that you have a spot where you can look in one spot and find them quickly, because I don't expect you to memorize the formulas for these. On a test, you'll always be allowed some sort of formula sheet. I'm the last one because of the weather, we didn't get the message out, but you will be allowed one sheet for the test, one sheet of notes. So why do we care? A little bit of foreshadowing to what's going to be coming up. Why do we care about factoring these equations? Well, I mentioned the word, so I should say factoring these expressions. I mentioned the word quadratic. I said quadratic form, where you have that x squared and then x and whatever. Well, there's something called quadratic equations. Quadratic equation is nothing more than an equation where you have the highest power of x is x squared, and the only other power of x would be x itself, or x to the 1. The simplest quadratic equation I can write looks like this: x squared equals 25. How would I solve that? Square root. Yeah. X has been squared, so to solve it, I take the square root. The square root of x squared is x. Now here's where we have to be really careful. What is the square root of 25? 5 or negative 5. So those are the two answers to that equation. However, not all quadratic equations can be solved by simply taking a square root. We might have x squared equals x plus 12. Bless you. I can't just take a square root here, because I can take the square root of x squared as just x, but what is the square root of x plus 12? That doesn't make any sense. So what I have to do here to solve a quadratic equation like that is, the first thing is I have to set it equal to 0. The way I do that is I move everything to one side of the equation. I usually want the x squared to be positive. Since it's positive here, I'm going to move everything over to that side of the equation. The way I do that, it's positive x, so I'm going to subtract x. So I've got x squared minus x equals 12. I'm going to do the same thing to the 12. It's a positive 12. I'm going to subtract 12. So this is x squared minus x minus 12 equals 0. Once we have it like that, our second step is going to be to factor. This factors. Into x plus 3 times x minus 4. Once we have it in that form, there's something called the zero product rule. Now, most of you have probably seen the zero product rule in its simplified form, which is just anything times 0 equals 0. But the zero product rule has a more important, more useful form. And that is, if a times b equals 0, then either a has to be 0 or b has to be 0. So what this is saying x plus 3 times x minus 4 equals 0, that's saying either x plus 3 equals 0 or x minus 4 equals 0. I now have two simple linear equations that I can solve. How would I solve this first equation? Subtract 3. X equals negative 3. How would I solve this second equation? Add 4. X equals 4. Those are my two solutions. I would then test them back in the original equation. If I put negative 3 in here, negative 3 squared is 9. Negative 3 plus 12 is also 9. That works. If I put a positive 4 in there, 4 squared is 16. 4 plus 12 is also 16. That also works. So the solutions here were x equals negative 3 and x equals 4. By the way, I could have done the same thing over here. X squared equals 25. I could have set that equal to 0. I would subtract 25 from each side. I have x squared minus 25 equals 0. Can that be factored? Yeah, it's the difference of squares. X plus 5, x minus 5 equals 0. So this one is telling me that either x plus 5 equals 0, or this one's telling me x minus 5 equals 0. When I solve them, I subtract 5 to get x equals negative 5, or I add 5 to get x equals positive 5. So people ask me all the time when I do the square root, is it wrong if I just said x equals 5 and forget about the negative 5? And the answer is, yeah, it is wrong. You do have to have both answers. So, homework 7C covers what we did today. So you should have homework 7A, B, and C done for Monday. And of course, quiz 7 also comes in there. We have one more week, 3 more classes, and then we have spring break. So a little time to absorb and maybe catch up on other stuff if you need to. When we come back from spring break, we will have 6 more lectures, 2 more weeks of classes. Then we have our Unit 2 test coming up in week 11. So I would recommend, I'm not going to give you any extra homework over spring break. We're just going to have our regular assignments. You know, it'll be homework 8, A, B, and C, and quiz 8. But I would recommend that if you have the time to download that study guide for test 2 and work on that over spring break, just as a review. Okay, you guys have a great day. We'll see you on Monday.